How about that?
Let's start again.
All right. So, hello and welcome to the SEVA VentRounds. Today is February 24, 2026, and the topic for today is targeting matters. We're going to focus on recognizing the tag, amongst other things. There is no endorsement of any mode, ventilator, or manufacturer. Whatever we say, it's our opinion. And there's Rob's and my conflicts of interest for you to be aware. Now, today, visiting from our Aurora Medical Center, we have Vlad. Vlad, say your last name because I'm going to destroy it.
Oh, you said it completely right the first time around. It's DF.
Oh, I felt so self-conscious that I said maybe I said it wrong. So I'm glad that I said it right. Yeah. So Vlad is our SEVA instructor, and he's going to be with us today and running through this. So that's wonderful, Vlad. Thank you for joining us. Remember, this is a recorded session. Keep your microphone muted. And if somebody wants to comment, you can unmute your microphone if you want to chat through this. And otherwise, if you do not want to say it and be recorded, then use the chat function on WebEx. Remember, there's a CME for the CCF crew, and there's CRC for every respiratory therapist that is joining us. All righty. Just remember to complete your evaluation after it. All right. I just want to rapidly highlight that the key part of what we do is we have this taxonomy, which helps us understand what the modes of mechanical ventilation do, essentially a generic name. And this is the life work of Rob Chatburn here, creating and developing this, and then working along and with the SEVA program to expand this and implement it clinically at the bedside. And the marvel of this is that it's simplified by every mode of mechanical ventilation has a control variable, a breath sequence, and a targeting scheme. Those are the three parts, the three building blocks. And a key part, which now is essential, but back then when ventilators were made, there were no computers. It was all mechanical devices and electrical devices with very minimal programming on them. And as they have evolved, now they have computers in them. And the targeting scheme essentially talks about how we program and interact, make the ventilator interact with the patient. And there are 7 targeting schemes that have been described, and many of them fall within one of these 7 categories. And then if we join those 3, you get the famous tag, which is the generic name for all modes of mechanical ventilation. Rob?
It's good. Good summary.
All righty. So here is your gift, Vlad. All yours.
All right. So with that nice introduction into tags, I hope that we can go over this waveform all together today and figure out what the tag is and what's going on with the patient. So please post your answers in the chat as we go along. So we'll start by identifying the tag based on the waveforms. Just remember that when we use a flow, looking at the flow-controlled breaths, we're looking at the pressure waveforms. And with our pressure breaths, we'll look at the flow waveforms. So go ahead, please look at this waveform, try to internalize it, and think what type of tag corresponds to this. Is it volume or pressure? Is it CMV, IMV, or CSV? And what targeting scheme is used? And go ahead, take your time and put the answer in the chat. We'll give it 30 seconds.
And by the way, just for those of you that are using the vent mode map, this would be a servo I ventilator from Gettinge.
All right, I see some answers coming through. Go ahead, submit yours. All right, even if you haven't posted, I hope you spend some time thinking about it and have some answer in your head. So I see some answers in the chat. There are VCIMV4DD, VCIMV2DA, VCIMV-BON4DD, but that's a typo. Okay. Well, there are a few answers here. And again, let's just walk through this waveform and see what it is, because admittedly, it's not the easiest one. So here we have patient and machine-triggered breaths. So let's take a look how the ventilator behaves when the trigger is done by the patient. So the first one, where the cursor is right now, we are looking at the patient-triggered breath. On the flow waveform, there's this red blip at the beginning of the breath that indicates patient probably had a flow trigger, and we see the breath. Now we're paying attention to the flow waveform that appears constant, but there is something in the middle of that flow waveform that interrupts it, and then the flow continues after that. Eduardo, I think we lost the flow waveform for a second.
Yeah, sorry. I just had a moment of peace. There you go. Sorry, we're back.
All right, excellent. And just looking at the pressure waveform concurrently, we don't really see that nice square waveform that we would expect if it was a pressure breath. So I think everybody was kind of on board that this is a volume controlled breath. Now the next question that comes in, is this going to be IMV, CMV, or CSV? So for that, we need to understand how patient behaves when patient-triggered breath and machine-triggered breath occur. So we already evaluated patient-triggered breath, so we can skip the second breath and move on to the third one, which appears to be machine-triggered. So again, it starts with a flow. Looks like the flow delivery goes on, and then there is a positive more flow for a little bit of time, and then we go back to the baseline flow, and then the breath is cycled. So again, it appears very similar to our original breath. And I hear most of the answers in the chart are IMV. And if you thought CMV, I don't want you to feel bad, because that's what I thought looking at this waveform as well for the first time, because the breaths appear very similar, but those little waveforms that happen in the middle of every single breath, just notice how a little bit different every one of them is. One of them are a little longer, one of them are a little shorter, and this deceleration looks different. So those are patient efforts. And you can see on the pressure waveform, there is a concurrent distortion of the pressure waveform down that corresponds to this acceleration in flow. And how the inspiratory time on each breath is actually a little different, because to deliver the flow, the ventilator will now need to adjust the time, because it's a volume control. So to keep flow the same, the inspiratory time needs to be adjusted to account for those little inspiratory efforts of the patient on top of the breath. Eduardo, Rob, would you like to add anything to this part?
So this is a great comment, Vlad. so if when we think about the breath sequence, you said very elegantly that this, if you look at this would look like CMB, right? So and to do that, I always like to do what you were saying, is to look at each one of the breaths and start by saying this one was triggered by the patient. This one was triggered by the patient, but cycled by the machine, right? And this one, I'm not going to take a look at this one because it's incomplete, but this one is machine, 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 machine. So all of these are mandatory breaths. So if you were looking at just this piece of information, you are absolutely right. This would look CMB, correct? However, we know, and that's why we use the bend mode map, that if the breath is long enough, then what would happen? So if the breath was long enough, then you would have a spontaneous breath. It would cycle on its own. And that's why this is turned into an IMB. Right, Vlad?
Yeah, no, I think that's
Yeah.
exactly right.
So that's an IMB. I'm going to show you. Do you think that should I show them the example? You want to show the sequence on that one, perhaps?
Yeah, no, I think that's a great example from the Servo U ventilator, where we can look at this admittedly very disorganized appearing waveform, but believe it or not, we can still obtain useful information from it thanks to taxonomy. So here's the breath, and it's triggered by the machine. So it's a mandatory breath, and then it's cycled by the machine as well. Then as we go to the next breath, we similarly gonna skip it because it's interrupted in the middle, so we can't really interpret much here. And then we go to the next one. This one was actually triggered by the patient. So there's a flow trigger, patient, and then we see continuous flow and the pressure goes up. And then pressure remains pretty stable throughout the breath at some point, and the breath extends far beyond the I time that you would expect from the mandatory breath. Because remember, the mandatory breaths, they will have to be patient triggered, patient psych, and the mandatory breath have to be either machine has to trigger, or patient can trigger and cycle would be by the machine. So, but this breath was triggered by the patient and cycled by the patient. And we know it's cycled by the patient because the extent of the breath was much more, so I time was bigger, and there is a flow that is cycling the breath. So patient triggered and patient cycled breath called spontaneous breath. And I see, again, Rob's comment on chat, volume cycle changes to flow cycle. So again, that's a key point, right? So you cannot, you should have a flow, if you have a flow cycle, that would be patient characteristics. So it will be a spontaneous breath.
Well, there's one minor point that you don't see here. If the patient took the big effort at the middle of the breath somewhere, but it was machine triggered, it could be patient cycled, but still machine triggered and still a mandatory breath by classification. So it has to be like you see here, both patient triggered and patient cycled to actually be a spontaneous breath.
Yeah, and then there's a great comment in the chat as well that this is IMB4, right? So IMB4 is when your individual mandatory breaths may be suppressed by the inspiratory effort of the patient. So I think that's exactly why we are saying this is IMB4 and not necessarily any other IMB. Okay, that's great. Anything else to add, Eduardo?
No, that's absolutely right. So I think that a message for the team in general is that if a patient is paralyzed, the breath sequence will always look like CMB, even though there may be behind that an IMB. Or if the patient is sedated or kind of passive, or you may not even be able to see what actually is happening. And this may be if they may all look like spontaneous breaths, and but the sequence is IMB. So in reality, doing this type of analysis to put the name of a mode and what actually does, what is the generic, takes reading the manual, doing a very detailed analysis to ensure that we are naming the things right, and then actually so in general terms, the message is that what you see on the screen may not reveal the full extent of what the ventilator does. And that's why using the Rosetta Stone or the ventilator mode map can give you the answer.
Right. All the great insights. There's a comment in the chat. Looks like spontaneous efforts occurring during the mandatory breaths that were insufficient to activate a volume support breath. Auto mode future would switch it from volume control to volume support breath, if enough to activate the trigger threshold. Eduardo, can you comment on that?
Yeah, I think that you're trying to refer that that if the patient had triggered the breaths, that this would be volume support. If that's the case, not in this mode. This is another aberrancy that occurs, which is in the older types of servo ventilators like this one. There used to be this button up here, which is called auto mode. And if you click it, you change the mode to what the person in the audience is saying, is that if auto mode is active, then the spontaneous breaths would be volume support breaths. So and it's a different type of tag, which is also very important. So even though it says volume control here, if this button was active and this little square was green, I think it's green or pink. Anybody can correct me on what the color is. I think it's green or pink. But if it changes color, then this is no longer just regular volume control. This is volume control IMB type 2 SA. So the importance of taxonomy becomes even more relevant. Vlad, great comment from the audience.
Yeah, no, that's great. So now we have left the targeting scheme to sort out. So what is a targeting scheme here? So let's see, we have a option answers the DD, DA. So I think we just addressed why it's not actually A for spontaneous breath. It's actually D. So I think we can confidently say here this is VCIMV for D, correct?
Yeah.
All right, very good. Okay, well, let's move on to how patient reacts to this mode. So what is the actual load? So let's start with inspiration. Actually, why don't everybody think about it and post what's the load during the inspiration and what's the load during expiration at the same time. Go ahead, post your answers in the chat. Options are elastic, resistive, or PMUS, which represent patient effort. All right, I see some answers coming through. So again, if you thought PMUS, again, we are talking about the inspiratory load right now. So again, remember we are in the volume control. So we are controlling the flow. So now we're looking at the pressure waveform. And when the pressure goes down like this, and then there is a increase in pressure that ultimately results in peak pressure of 36, and it starts from the peep of probably at least 10. We see that number 1 of peep on the right side of the screen. But that tells you that all this area of the pressure, this one is a PMOS. It's all muscular effort. You would expect this waveform to look a little differently if patient was passive on the ventilator. And because of this patient effort in the middle of the breath is pretty distorted right now, so it will be hard to judge if patient really has elastic or resistive load during the inspiration. All right, and now let's talk a little bit about the load during the expiration. So what everybody thinks, what's the load is during the expiration here? And there is great comment about this initial step that doesn't seem to be very high on the pressure waveform, that step up in pressure, and that the resistive load is probably not very high. And during expiration, when we're talking about the load, we always want to remember our time constants. And if our expiratory time, which is patient has a respiratory rate of 32, so we are limited on how much expiratory time we have in this breaths in general. So even though the return to the baseline, looks a little prolonged, but in the context of the expiratory time it takes, we see this seconds marked on the white baseline. So it actually takes less than 1.5 seconds to return the breath to the baseline. So probably not very high resistive load. If anything, would be elastic load or normal. Okay, excellent. And then there's another thing that we can highlight here during the expiratory waveform, that the patient muscular effort actually continues probably a little bit beyond the breath. Will you agree, Eduardo, that we see a little bit of muscular effort here going beyond the cycle?
This is important. You refer to these little notches?
Yes.
Yes, those I marked them because this is a source of common confusion with our teams. These little notches usually are artifacts. If they are more marked, like if I put it like that, that definitely is evidence of PMOS. But when they're that tiny, like these ones that you see here, usually it's a artifact of, as we depressurize, the ventilator is trying to keep the pressure at the PEEP level, and you're gonna see these little tiny, so if they're repetitive, always at the same time, and without clear evidence of PMOS at the end of the breath, like you see on this breath, there's no PMOS at the end of the breath, but you still see it, that would be consistent with an artifact. So I hope that helps.
No, that's a great point, Eduardo. Thank you. All right, and finally we are moving to our PV discordance. So do we have a normal trigger, or do we have any problems with the trigger? What does everybody think? Helpful to remember where the patient effort starts and relative to the ventilator. Again, I think early trigger, yeah, I would agree that the early trigger is a correct answer here. So as we can see, the patient effort starts later in the breath. We see evidence of PMOS starting a little bit into the breath, and we see it on the pressure waveform. We see that concurrent increase in flow in our flow waveform. So the breath was triggered by the machine and has already been going for a little bit before diaphragm kicked in. So that would be the definition of an early trigger, and that will be primary PV discordance here. All right, and then any PV discordance during the inspiration, assistance, over assistance, or under assistance.
So excellent job. Vlad, do recall that whenever you call the first discordance, the rest are just going to be manifestations of your first one. So that's an important thing. So even though right now you're going to call something during inspiration, be aware that that is a manifestation of the first discordance that occurred. And so if you see early trigger in this case, we usually do not call the next ones, although it looks like what I hope that you are going to call. So I cannot see what they're calling it, Vlad. What did they call?
I
what
see one answer is assistance. So far, anybody feels any different, please post your answer in the chat. But yeah, thank you, Eduardo, for reminding about that yes, once we identify the primary problem, we don't need to be searching for others before we fix it. And if we fix the right problem, then things will look better. Some work shifting, but not severe. Yeah. Patient's effort is so consistent. Yeah, great. So again, yeah, assistance during aspiration. Yeah, there is some work shifting, but again, because the pressure doesn't really drop below the peak that we already set, it's not overly excessive work shifting. Excellent. All right, so we'll be wrapping up.
Yeah, so I just wanted to make a comment that in this case, the dual targeting, which changed from volume to pressure, allowed or minimized the drop in inspiratory pressure. And you can see that the PMOS occurred at different parts of the breath throughout these 5 breaths that you have in front of you. But and it definitely distorted the pressure waveform. But it didn't drop it below the baseline. And I think that your observation that this is not under assistance because of that is key. It doesn't drop below the PEEP. And the reason why it doesn't drop below the PEEP is because the ventilator has this dual targeting that avoids that. I would also highlight that under these circumstances, the engineers, as you clearly mentioned, Vlad, shortened the inspiratory time to maintain the tidal volume the same. And you can see that tidal volume remained, even though in the presence of work shifting and assistance, they kept the tidal volume at the target that the patient had. And so this is engineering that, even though when we read this, I sometimes have a natural reaction of saying, oh, this is not volume control. I want volume control. I don't want to use anything else. But you can see how in this case, for this particular patient, the ability of the patient to the mode to change avoided the patient from a situation in which it could cause severe under assistance. And obviously it has to do with your goal and whatnot, but at least on these circumstances, the mode is doing what it was designed to do to prevent. Rob?
Yeah, to state it another way, a plain old volume control just serves the goal of safety because you get the same tidal volume every breath, but it doesn't serve the goal of comfort because the patient has a lot of work shifting. If you add in dual targeting, and particularly with this situation where the inspiratory effort is not big or long, then now you're serving the goal of comfort as well. So that is an advantage. Of course, on the next slide, when the patient makes a huge effort, then safety goes out the window, right? Because you get a massive tidal volume.
Absolutely. And you could argue that this is bad, but you can also argue that it prevented the patient from having three breaths in a row. At the same time, I would argue if the goal for this patient is safety, then the patient is likely under sedated, or we have to deal with whatever is causing this. And if your goal is comfort, then it's in the wrong mode. Alrighty. Vlad, what would be your take-home messages? What do you want the team to take home?
Yeah, no, I think the key points is that pay fine attention to what's happening to your waveforms, your patient, right? Because I think IMV can look very much like CMV, but those nuances in behavior, when you see that, you know, your flow is not constant, and be, you know, in the middle of the breath, just be aware that your machine can be shifting between volume and pressure delivery and dual targeting modes, and that can really affect how you know, you achieve your goals of comfort or safety, and overall in the event of the strategy.
Perfect. I love that. Rob?
The key here is that you have to understand what dual targeting is. As you said in the title, targeting is everything. It can change the mode, and you simply couldn't explain what's going on if you didn't understand what dual targeting was. You couldn't explain a little hump in the flow waveform.
I love that. And it's not an explicit thing. So it's not like you're going to grab the manual and it's going to say, oh, this is a dual targeting. They will use other words to explain what the mode does. In some manuals, it explains it rather well, but it uses words that perhaps are ambiguous to the clinician. For example, the term flow adaptation, very romantic, but it's not telling you that it's changing from volume to pressure, and it does tell you that the patient may receive larger tidal volume than what you are aiming for. So key important points for you to be aware of. Thank you very much. Here is the CME for the CCF caregivers. Use it because it's for you. The CRC for the RTs. Demonstrate that you're keeping up, learning and growing. Join us at the SEVA program. Our SEVA Summit has reached capacity. There's a waiting list, so don't be shy and put your name there, because if anything opens, we're happy to have you. And I want to thank Vlad for running the SEVA VentRounds today. And this is a manifestation of how we are joining and growing amongst our centers. Great job, Vlad. Thank you very much.
Good job, Vlad.
Thank you, Eduardo, for your mentorship. Thank you, Rob.
All right, team. Have a great day and stay safe. Bye-bye.